Okay, so geometry, chapter 1. And if you open up your book to page 2, the first thing you get to see is a picture of toiletries. So what does toiletries have anything to do with math? Oh, very good, elements. And you notice that the section says sets and subsets. Okay, that seems kind of self-explanatory. But we're going to go into depth as far as what this actually means whenever you have a set and what a subset is and what their relation is. Because there are distinct relationships between these. But what's interesting, what we're going to find with geometry, especially whenever we compare it to other maths that are out there, or the math subjects, topics, that geometry is going to be more easily related to the everyday world than, say, your Algebra 1, Algebra 2, or even some of your pre-algebra. Some can, and you do, but this is going to be a little bit more easily related. And so that's where we're actually going to go through this chapter, but then we're going to take what we've learned and we're going to apply it to kind of the real world. So, looking at these toiletries that we have here, okay, if you see in your book it says, do the objects shown have anything in common? What do you think they have in common with each other? Anybody?
They're all used for hygiene.
Very good, they're all used for hygiene. Okay, so they have a relationship. Let's be, what do you see on the page here? What do they have in common? Because that's actually a really good point, and what's interesting is we're going to be able to relate things from different perspectives, and it all depends on how you actually view it. And what's interesting is one person, and this is what I love about teaching and about discovering too, is one person will see it one way, and then another person will see it from a different point of view, and that first person will be like, oh yeah, I didn't even think of it that way, and vice versa. The second person will be like, oh, I didn't see it from that side, but I see it from this way. So hygiene, that's a perfect example. These are all used for hygiene. You have soap, toothbrush, toothpaste, shaving kit, things like that. What else specifically do you see them, like physically? What do they have in common?
They're in a basket.
Absolutely. They are all in the same basket. Okay? Now, you may have, say, the toothpaste sitting outside of the basket. Okay? And yes, they all have a relationship because they're used for hygiene, but that toothpaste is not part of that group that is within the basket. Okay? And so those are kind of some of the relationships that we're going to be talking about. All right? Some of the differences and commonalities. Now, whenever we talk about let's say this basket and it has these toiletries in it, that is going to be called a set, okay? A set or group of items. And if you notice under example 1, it's going to label the basket as set C, capital C. And then it lists all the elements inside the basket in brackets. So we have the basket of stuff, and it is going to be set C. And then we're going to see an equal sign, and then we're going to see some brackets. And then within these brackets, this is what we list as being all within that set. So we will have the toothbrush, the toothpaste, the razor, soap, and so on. And then you close the brackets. Those are all the elements of that basket. What is it that is contained within that basket? Does that make sense? Easy enough, right? So, now, the same as we read below that, the same set can be described using set builder notation. And let me read off what this says first. The general form of set builder notation is this. okay, where X is an arbitrary element of the set. This vertical, so this first X is some element of this set. It can be any one of those. Okay, this bar indicates the words such that, okay, and the vertical line is followed by a description of a representative of elements of the sets. So, in example 2, if you use the set builder notation to describe set C, then we're going to see set C equals, okay, and what does X stand for again? Yeah, well, an arbitrary element. So any one of these elements, okay, we can talk about any one of these such that that element is, and then it's part of that whole set, okay? You will see this some. What's interesting is we won't necessarily talk a whole lot in terms, but we're going to utilize it during this chapter so you can become familiar with it. The biggest thing to remember in math in general, we use symbols, numbers, and letters to help us communicate. Okay, instead of writing out a paragraph of all sorts of things in words, we actually use symbols. And so as we use these more and more, you'll become a little bit more familiar, okay, with what these symbols are. So notice these brackets means that we're containing something, but whenever we talk about the basket or set C, that equals, and you can use any one of these elements, say the toothpaste. Toothpaste, such that the toothpaste is an element of all of these, or part of that entire group. Okay? Now what that helps us do, is we get to talk about toothpaste as a relationship to everything else that is in that basket. Okay, we're specifying, let's pull toothpaste out and let's discuss it for a minute and how it's involved. Make sense? Okay. And that's all geometry. In fact, the year's over with, so calm down. So now, as we move along, the set C is the set of all elements. Okay, all elements. Now, whenever we talk about elements, this is a very important symbol. It's kind of like an elongated E. If you took an E, grab these three, if you could loop your fingers into the ends and stretched it out some, that's what it would look like. So we can say the comb is an element of C. Okay, or whatever that whole set is. Now, be very, very familiar with this. Okay, this is one of the symbols that you're going to need to remember because you will use it a lot. Okay, so this right here means it is an element of some group or some set. Now, here, whenever we talk about the equal sign, equals is, we all understand what equals means. One thing equals another. 1 equals 1. 2 plus 5 equals 6, right? So, what? See, one person caught that. That's really good. No, 2 plus 5 does not equal 6. If we need to, we can go back to some earlier mathematics and get concrete in those if we need to. So as a reminder, I will be making mistakes on purpose up here, so it'll be important for y'all to pay attention. And what I look for is, no, that ain't right. So y'all be ready for that. So yes, 2 plus 5 equals 7. So here, if you see, remember that the symbol for equals means is the same as. Okay, now whenever we're talking about geometry, sets, groups, and elements of sets, the equal sign means that two sets are equal if they have the exact same set. So let's say that you two ended up having the same basket with the same stuff in it, well then your morning kit is equal to each other, all right? But if, let's say you have the same basket, but you are missing soap because you just disagree with soap and don't think that you should ever use it. Well, now it does not equal theirs because there's even one element of it that is different than everyone else's. Okay? I know it's simple and elementary, but we want to make sure that we kind of wrap our head around what the equal sign is actually talking about. Now, what I want to do is look further down, and you're going to see this symbol. That symbol right there, it's kind of an elongated C with a line underneath it. Okay? Look through, and what does that stand for? Can anybody tell me what that symbol stands for? In between example 3 and 4. In the paragraph in there.
Subset?
Yes, very good. Awesome. A subset. So we're talking about sets, and then you have a subset. All right, now I want y'all to write this down because this is going to be very important. I know it's in your book, but let's write it down anyway. If set A contains set B, okay, it contains set B. Now let's talk about that for a second before we move on. Let's talk about the toothpaste. Okay, the toothpaste is an element of that entire basket. Okay, that set. Okay, the basket being a set. Now that toothpaste, are there elements that are contained within or on that thing of toothpaste? Yeah, we can talk about the toothpaste and all sorts of different aspects of it and things that are in that particular toothpaste that might not be in another set of another tube of toothpaste. Okay, the way it looks on the outside, what it has on the inside, things like that. There are elements within it. Okay, so now what we're talking about, let's say the toothpaste, is a subset of the whole set. Okay, it's an element, but that set of objects, because it's not the same toothpaste as another. You can't just throw any toothpaste in this. It is this specific particular tube of toothpaste that's in this basket. Okay, makes sense? All right, so if set A contains set B, then set B is a subset of set A. And so we write B is a subset of A. Okay, so all of this is actually, and the group and all the elements within B are contained inside of A, so then B is a subset of A. So this is subset. Now this is very important. It seems redundant, but I suggest you know this. In particular, every set is a subset of itself. Okay, so A is a subset of A. Now, why do you think it's important for us to discuss this or even recognize that this is true?
Because it's a set on its all on its own before you add other stuff into it.
True. It is. Okay, now who disagrees with this, that A is a subset of A? Meaning that it is, all the elements of A are contained within A. I mean, it's kind of like, well, yeah. It's like I'm standing on a carpeted floor that is carpeted. It's the Department of Redundancy department. You'll get that?
Mhm.
Okay. So now it seems redundant, but what this helps us accomplish is the definition. We are substantiating what the definition of a subset is. So if we are saying that all elements within B are a subset of A, well then we have to recognize that A, being a set, can be a subset of itself. Okay? So all this does, again, is just substantiate the definition and this concept. Now, a couple more elements that we need to know is you have what's called an empty set or a null set, N-U-L-L, empty set or null set. And these are, keep that up there. These are denoted by either, you have two brackets like this, and what I commonly use and what I think you end up seeing more often than not is this. It's a circle with a slash across it. What helps with the slash is the slash indicates that if you have this, well now you don't have any of it, okay? So this would be a null set. So what if we said that nail clippers are not in that basket. So we say nail clippers are not an element of C. How do you think you would write that? So nail clippers. What do you think this symbol would be, not an element of C? Okay, well that's a null set. That means that there is no set contained within another set. Okay, that means there's nothing there, or there's a set that is totally empty. Now, and what's important with geometry is you hear the words that are being said because each of these have definitions. We talked about what an element of something is, and there's a symbol for element. What if we said clippers is not an element of C?
Do the circle and then do the little C with the line underneath it?
Okay, so that's like this one?
Yeah.
Okay,
So
that's a
it's not
subset. That's a subset. So what is element? What's the symbol for element?
The E.
The E thing, right? So we have the E thing here. But here we're saying clippers is an element of C. Now we just talked about using this line to kind of say it's the opposite, or it's not what we're talking about. So what could we add to this to say that clippers is not an element? Absolutely. We'll put a line across it like that. Not an element of. Make sense?
Yes, sir.
Awesome. Now, I'm going to throw y'all back a little bit. Whenever we're talking about a null set, okay, or an empty set, so again, what this is saying is that there are no elements. There's nothing that exists in that. Now, by definition, an empty set is considered to be a subset of every set. Okay, so if we're talking about, like we were here, set A, if B is a subset of A, okay, A, by definition is a subset of A, well then also a null set is a subset of A, or whatever we're talking about. A null set is always an option. So if you think about it, you can have that basket and ultimately you could remove everything out of that basket to where there are no elements in there. That's possible, right? Even if you glued them in there, you could get like a crowbar and a hatchet or something and just, rip that basket apart and eventually get them out of there, right? Is that what you do? I do that. Are y'all angry in the morning? Y'all get like really angry in the morning? It's time to get up and then you start slamming your stuff around. Next thing you know, you made some huge mess. We'll get back onto geometry. It actually is geometry, interestingly enough, but we'll talk about that later. So understand, by definition, a null set is a subset of every set, okay? Or a subset is a null set is a subset of A in this particular situation. Alrighty. Now, if you turn to page 4, you're going to see these. We're going to just go over these definitions really quick of these symbols. And make sure. So, we have let's review real quick. What is this? What does it stand for?
Element.
Element of is an element of. Okay, what about this?
Not an element.
Okay, is not an element of. Then we have this. What does that stand for?
Subset.
Subset. Okay, or is a subset of. What about this? Do you think?
Not a subset.
Okay, is not a subset of. And as you write these symbols and you apply them, read it. It's probably going to help you if you kind of say it out loud to get it going through your head and you're reading it like you are a sentence. Okay, these are all mathematical sentences just in a different way than what you're used to. Then we have this. Do you remember we started off with what this is? This is not a C, this is kind of an elongated.
Is it a proper?
Yeah, you call it a proper set or a set. But yes, it is a proper set. Okay. And likewise you have is not a proper set. So you kind of understand where this line coming through can be applicable. Okay? Does that make sense? Awesome. Now finally, the last, well not the last, but the next one we're going to be doing for right now is this U. Okay, it looks like a capital U, but there's not this piece that comes down typically. Alright? Now, this is going to be what's called a universal set. Okay, you're going to hear me relate or talk about this. You'll hear me say universal set, but then we'll also talk about a universe. Okay, now a universe doesn't have to be with all the planets and stuff. You could make this room and just talk about it, and we can talk about this as a universe or a universal set. Okay, and then find out what is inside of this and related to it. So let's do that real quick. We have, let's just look at this wall. Okay, we have this whole wall here. What is part of the wall? Okay, if this whole wall is a universal set, what elements do we have on the wall?
Parking.
That also.
Okay, so we have a plug, the what thing? Okay, so we have this gray bar. We've got plugs on the wall. What else? Okay, we have the board. So we have all these pieces that are part of that wall, okay? Now we have, if we talk about a plug, okay, and I'll draw it up here too, even though now this is not part of the board, we're just talking about the plug. And you even have That's what holds the faceplate onto the wall, is a little place for the screw. Okay, so here we have this plug that is part of the wall, and then we have this dry erase board that is part of the wall. Okay, and this wall is the universal set. Now what's interesting is this plug has elements to it that this dry erase board does not have, and vice versa. Does that make sense? Okay, so here we have this whole wall, and we've got two different things, and then we can talk about just this plug. We have the electrical inlet, we have the faceplate, we have the screw that holds the faceplate, we've got whatever wires are attached, and so on. We can talk about all those elements of this electrical plug that have nothing to do with this dry erase board, but is still part of the whole universe. Okay, or this universal set. Likewise, the dry erase board has trim, it has this black molding, some way probably adhesive that keeps it up on the wall, but then we have the black marker that's on it, the little lip, and even these. I mean, all these different things that you start looking at, and as you start digging closer and closer, you're like, wow, there's actually more and more and more to this. Even going to the part where there's a crease here, and you got some red marker that didn't get wiped away and things like that. There's all these elements that exist, and the more you pay attention to it, the more we can discover. So notice that even though we're talking about this whole wall, we can actually take pieces or sets or subsets of that wall and just talk about it. Okay? Now, as we move along here in a little bit, we're going to talk about what relations some have with each other, because sometimes we come across situations where two items on in a universal set actually share elements with each other, but then don't share some elements with each other. And we'll be going into that. Any questions so far? Okay. So let's turn to 1.2. We spent a lot of time on this first one just to get the ideas down. We're actually going to be moving faster through the rest of these. Okay? I'm going to set this right here. Has anybody heard of the term Venn diagram?
Mm-hmm.
Have y'all used them before?
Mm-hmm.
Cool. The most common way that we're going to see a Venn diagram is it's going to be a big rectangle, and that's going to be your universal set. So this U identifies, we're talking about everything inside this box. Okay? Then you're going to have two circles. Now, the circles can be anywhere on this. Okay, think of like two, if you want to, two plates or discs that you're moving around. Okay, so sometimes they will actually connect, because when we're talking about A and B, this will have, and we're just going to use numbers, it'll have 1, 2, 3, 7. This may have 4, 5, and 9, but they're going to share 8 and 10. Now what this means is the elements of A, okay, the elements of A are going to be 1, 2, 3, 7, 8, and 10. B, the elements are going to be 4, 5, 8, 9, and 10. Okay, so two different ways to talk about these two. One, you can draw a picture, or two, you can list them out like this. Now what's interesting is both of these share 8 and 10. So whenever we draw it, then we have to overlap those circles so that it shows that they're sharing it, as opposed to writing 8 and 10 on this one and 8 and 10 on this one and keeping the circles separate. Does that make sense to everyone?
Mm-hmm.
Okay. So, just to kind of recap, these elements are not part of this set. Okay, and these elements are not part of set A. But 8 and 10 are elements of both of them. Okay, both A and B. Make sense? Awesome. So then, what's interesting now is, let's say we are talking about, we'll use our same example. This is our wall. The universal set is our wall. We have our dry erase board, DE for dry erase board. And then we have our socket, we'll say S for socket. Okay, now notice these don't interlap because, as we discussed earlier, that they don't have elements that are the same. Okay, they don't share elements with each other. So the dry erase board has markers, it has molding, it has the lip to it, adhesive, and so on. The socket has the plug, face plate, the screw to hold the face plate in, and say wires that are inside of it. Okay, now what else exists on this wall that we talked about?
Bar.
Okay, so we have this silver trim. Okay, where does that fit in here?
You know,
It needs to go in its own circle.
Okay. What does anyone else think? Agree, disagree? You agree? Is it just because of peer pressure? Is that what it is? Okay. So yes, it can go in its own circle, or if we're not breaking it up into smaller elements, then it can just be its own thing. So we'll say SM for silver molding, you can just throw this out here. Okay, so it is an element of this universal set, but does not have anything to do with the dry erase board or the socket. Make sense? And then even the paint, green paint, GP for green paint, you can throw on there too as an element of the universal set, but has nothing to do with these two. They're apart from them. So this isn't really difficult, but it is necessary to take time to kind of wrap your brain around this way of thinking, because it's a little bit different. Easy enough, right? Yeah, it actually is. If you're having difficulty with this, you need to get out of my class. I'm joking, that would be so horrible. All right. So let's go ahead and go
Can I
to,
ask something?
yes,
You said these in the middle are a subset of both of them, correct?
yes, they are a subset of both of them. Now, one thing that we want to do, this is what I forgot, I knew I was missing something. If you look in your book here, okay, the example of whenever we're talking about the numbers 8 and 10, how they were part of both of those, of both A and B. Now, we can say that 8 and 10, well, let me back up. I don't want to do that just yet. We can say that A, and I'm going to show you what the symbol is. What does this symbol mean here? If you can read in your book.
intersection?
Intersection, very good. So this right here, it's kind of like an A, or the way I write my A's without the A going across, or that line going across, stands for intersection. Okay, so you will need to know that. You will use this a lot. And if you think of intersection like a street intersection, you have two roads that go their own ways, but they cross paths with each other. And what's interesting is that on a street, those intersections, those two roads, that intersection, they actually share elements with each other. They share the same traffic lights, the same signs, the same material, everything else. Even though they have the same material in their own stuff later on down the road, this is what they actually have specifically in common because that particular piece of the roadway is shared by both of them. That traffic light is shared by both of them, and so on. Make sense? Awesome. Sweetness. Now let's move to 1.3. All right, so what we are going to talk about right now, and we'll go through this quickly because this is actually going to be part of your homework assignment for you to research. But we're going to be talking about undefined terms and definitions. I'm going to read this off to you. A good definition must have the following characteristics to successfully convey the meaning of the term. Okay? First of all, it must be clear. So the definition must communicate the point and state the term being defined. Avoid vague or ambiguous language. It's like saying, we don't use white paint in here because that's whack. Okay? Or really, what does whack mean to, I mean, some people might understand, but it's ambiguous and vague definition or word usage. We're not going to use the term whack in any of our definitions. You can if you want to, but then you've got to define what whack means. All right? Useful. The definition must use only words that have been previously defined or are commonly accepted as undefined. So therefore we cannot use the word whack. Precise. The definition must be accurate and reversible. Identify the class to which the object belongs and its distinguishing characteristics. It must be concise. The definition must be a good sentence and use good grammar, as opposed to using grammar real good. Stick to the point and avoid unnecessary words. And then the objective. The definition must be neutral. Avoid emotional words, figures of speech, and limitations of time or place. Okay, so evaluate this definition in our example. Space is the set of all points. Okay, is this a good definition? Space is the set of all points. So let's break it down. To figure out if this is going to be a good definition or not, first we have to see, is it clear? Clear. The objective being defined is named in the definition. It is not ambiguous. Okay? It's pretty specific, right? Useful. Look at all the words in the definition. Have they all been defined? Okay, so far, space is a set of all points. We haven't really talked about space, but that's what this definition is identifying. What we haven't talked about yet, we haven't defined our points, which we're going to do in this chapter, and you're going to be learning. But once we do define it, then it would cover that. And then being precise, the definition clearly or describes space accurately. Then concise, the definition contains only necessary words and uses proper grammar. And then objective, this definition uses appropriate objective languages. Okay, so that's all good and fine. For your homework assignment, that's okay. For your homework assignment, you will have to list out what a proper definition is, okay? So you're going to have to go through this. It is important because in this section you will have to identify in your homework what is a proper definition and what is not a proper definition and why. It is really only in this section that you're going to do this specifically as far as definitions. We're not going to do this throughout the whole book. However, with geometry, have you ever heard of the term proofs? Yes. And that's exactly the same facial expression that everybody makes. I have not seen one person go, proofs, yes, I've been waiting for those. Whenever you hear geometry, everybody hears the word proofs. And immediately they're like, oh. And they're a beatdown. They are necessary because then you know that you are doing the right thing for the right reason. Proofs are also very important because it forces you to take one step first, and then the next step, and then the next step, and then the next step. And whenever you make a mistake, you can go back and look over your process and identify exactly where you messed up. So that's the value of them. So I'm going to front load our experience in this book, or in this class, by saying we will be doing some proofs, but it's only to reinforce that. But then whenever we're done with that, we're done with proofs for the rest of the, pretty much for the rest of the year. Okay? So, now, the reason why I bring that up right now is with this term definite, or these definitions that we're talking about, it's important to understand what it's saying for the right reasons. Because think about how many definitions we have in math that we use, right? So we use a lot of them, and they dictate what the majority of people end up doing. If it was vague, then that would mean that each of you would interpret it differently and end up doing your own thing, and we'd end up with different answers. Just even though you're reading the same definition, right? So, it's like, okay, the definition of the color of this trash can is going to be dark gray. And each of you make this plain trash can dark gray using your own stuff. How many different shades of dark gray do you think we'd come across? A lot. I guarantee you, every single one of you would have a different shade of dark gray that would come to mind. And so that's kind of the point behind all of this. It has to be this specific color tone with these specific elements involved so that the same color comes out no matter who does it. Okay? Alright, so within this homework, you're going to be given definitions, and you're going to have to identify if it was precise, not precise, or if it was good definition or not. If it's not, then you have to explain why it was not a good definition. Alright, and alright, page 10. This is very important. Very important. I can't stress enough to you how important this is. Other than, I mean, so important you might get tested on it later, I don't know. Just kind of throwing that out there. So, we're going to talk about a point, a line, and a plane. A point, a line, and a plane. Somebody point to a point. Okay? Is this a point?
Yeah.
Is that a point?
Mm-hmm.
Okay. Now, somebody read me the definition of a point. It's on there, in the blue. On page 10.
Spot an object with no dimensions, length, width, or thickness. A location in a space.
Okay, which is interesting. This point right here, do you think we could measure that?
Probably.
Probably.
If we really wanted to.
Yeah. I mean, it has some distance, some dimension to it, right? So when we think of point, we think of something like that, something really small, small dot. However, if you really want to think about this, that right there has countless numbers of smaller dots that are all in it or that could be fit inside of it. And in one of those dots, you could even go smaller, like expand it, blow it up, and do just a countless number more dots inside, which is interesting. So we started off, here's a point. But realistically, there are an infinite number of points within that one point. It's kind of weird, but But if we look at the definition, the point, or a spot, an object with no dimensions, length, width, or thickness, a location in space. All right. Now, in order to identify this, if we're talking about a point, it's some capital letter. The book uses the letter P, and there is a dot next to it. Okay, so it's point P. Okay, or point R, if you want to do that too. Point R, doesn't matter. Now a line or a straight line is an object that extends indefinitely in one direction or in one dimension, has length but no width or thickness. Okay, so here's a line. Now, if I were to draw a true line, where do I stop? According to the definition. I'll keep dragging it and dragging it. Where do I stop?
No one.
Exactly, because it goes on indefinitely, right? You want to see me do that?
Yes, yes, just.
Be here for a really long time. So, yes, so it goes indefinitely in both directions, but it has no thickness to it, okay? So now, a good way to think about this would be a laser beam. The way a laser beam is said, if you hit it, and it'll shoot off and it just goes off indefinitely and carries on, okay? And then finally, a plane. Okay, a flat plane is an object that extends indefinitely in two dimensions, has length and width, but no thickness. So, we have length here, we have width, but there's no thickness. If you look at a piece of paper, okay, this piece of paper would be a plane, okay? It just so happens this paper actually has thickness to it, but you can kind of relate to it. It's a two-dimensional object, not a three-dimensional object. So basically what would happen is as you look at it this way, you see it has length and width. If you were to turn and look at it this way, you wouldn't be able to see it at all because there is no thickness to it. It just disappeared. And then I'd bring it back. And then disappear. Bring it back like a magician. It's awesome. All right, so now whenever we talk about a line, the book gives us this description. We have line CD. Now we have two letters here because there will be 2 points that this line has to pass through in order to be a line. Okay, otherwise, how do you know what direction the line is traveling? Okay, you can have, point R, point S over here, but it just so happened this line traveled through points C and D. So this line is line CD. And then likewise, we have plane. And here it's, you see plane K. Now on the plane, the letter that is used is a lowercase letter. Okay, a lowercase letter. Alrighty. We're going to talk some more about those here shortly, or here after a while. We are going to skip 1.4 simply because they are your definitions and your homework. I want you to research and study them, and we will actually be applying them later on, okay? Because we're talking about collinear points, concurrent lines, coplanar points, things like that. The definitions are in here. And I want y'all to write out the definitions. These are important because you have to identify them on your test as well. Okay? But we will actually discuss them at a later time. So only do the research on that. That's 1.4. 1.5. Now, second. All right, from here we're going to stop and we're going to go outside. Okay, these last 3 sections, 1.5 and 1.6 and 7, we're going to be talking about, as you put your stuff together, I'm going to talk about what a postulate is.
Do we need the book?
Yes, bring your book, bring your backpacks, bring everything with you, bring something to write with, because you'll probably take some more, maybe take some more notes. We're just going to look at things from a different perspective. We've been in the classroom, it's time to look at stuff outside. Now, as we're gathering our things together, geometry is set up of definitions, postulates, and theorems. 3 different things. Definitions, postulates, and theorems. Okay? So, I'll start off by reading this real quick because we have a couple minutes and we're going to step outside because I want to go over this part before we go outside. A geometry in general is a system of definitions, postulates, and theorems that is built in a logical progression. Just what makes up good geometry is the question that's asked. So to determine that, the key is a set of postulates or basic assumptions. Postulates are basic assumptions, and those are different from definitions. Okay? Mathematicians desire 3 qualities for a system of postulates, and they need to be consistent, independent, and complete. Consistent, independent, and complete. A consistent postulate system contains postulates that do not contradict one another. Okay, so it's consistent, none of them are inconsistent or negate one of the other ones. Then you have independent postulates, okay, in which no postulate can be deduced or proved from the other postulates in the system. So it makes up its own setup. Okay, it does not require one of the other postulates to make itself true. Okay, so first it's consistent, then it's independent, and then finally it's going to be complete. Okay? There can't be something that is left almost unknown. So let's look at this, or listen to this example. If the animal is a parakeet, then it is a bird. If the animal is named Polly, then it is a parakeet. If the animal is named Polly, then it is a bird. 3 separate definitions that don't necessarily rely on each other, and they don't contradict each other, but they kind of create a complete setup. So if we have this bird, okay, and it's a parakeet, then it's going to be named Polly because we have 3 basic assumptions. If the animal is a parakeet, well then it's a bird. Okay, well if the animal is named Polly, then it's going to be a parakeet. And if it's named Polly, then it is a bird. And then you can go back to the first definition, or postulate, and it says if the animal is a parakeet, then it's a bird. They all basically complete a circle. Let me ask you this, if this would be an accurate one. Okay? God is love. Love is blind. Stevie Wonder is blind. Therefore, Stevie Wonder is God.
Is she really blind?
Yeah, Stevie Wonder actually is blind.
Really?
So, yeah.
Oh,
So you could put in any blind person in there. Now, what's interesting is you can create that as an assumption, but in reality, is that accurate?
No.
No. But you see how that works and where we're going with that. What's interesting is you can make up your own stuff like that as well. And it's really not that hard. All right, so let's pause here. Make sure we have all of our stuff, and we're going to go outside. All right, we're going to talk about postulates for a little bit more, okay? So we're going to read this first one, and it's called the expansion postulate. All right, a line contains at least 2 points. Okay, a line contains at least 2 points. So look out the window here. Somewhere out there, find a line.
The wall, the brick pillar.
Okay, so the brick pillar there. Okay, so what How are you able to define that that is a line?
Because it has a point up here and a point down there.
Awesome.
I want to measure it like that.
Perfect. Okay, good. Now, technically, a point has no space, dimension, or anything like that. But what you're explaining is that there is some connection that makes that line travel through a specific path. Okay, so that's one. What's another one? You're welcome to come up to the window if you want to. What's that? A line.
There's the white thing. The white line.
The white lines out in the parking lot? Sure. What's that? Another one? Look way out there, anywhere out there. Where do you see a line?
The metal things around the tree.
Awesome. The metal things, yes, around the flagpole. Okay, now theoretically, a line travels infinitely in both directions, but at the same time, the concept behind this is that you're seeing that you have some straight system that in order for it to get from one place to another or to give it direction has 2 points. Now, just like you were bringing up the metal here, direction had to be created by determining at least 2 points for that to travel through. Okay, so that's the importance of it. All right, so the expansion postulate is a line contains at least 2 points. It also says that a plane contains at least 3 non-collinear points. What do you think non-collinear means? Okay, they're non-collinear. So let's think about it this way. Collinear points. That means if you have 2 points that are collinear, then they can help a line be determined. Okay, so 2 points and a line is able to go through both of them. Okay, so 3 non-collinear points would mean what? That a line could not go through all 3 of them. Okay, a line might be able to go through 2 of them, definitely going to be able to go through 1 of them independently, but it's not going to be able to go through all 3 of them at the same time. So if you think about it, if you look at the parking lot out there and there's a line that goes to the right and the left and it kind of disappears in both ways. So you could say that you could identify 3 points on that white line out in the parking lot, right? And that line goes through all 3 of them. Those are collinear points. Non-collinear points would be like looking out here in where this flagpole is and picking 3 rocks that are in separate parts inside that rectangle. Okay? If I told y'all to go, all 4 of you or 3 of you or even 8 of you, most likely, if you went out there and I said just point your finger on a rock, y'all would end up pointing to rocks that a line would not be able to go through all of those points. Okay? So now what happens is, if you think of taking since you can't take one line to go through all 3 of those points, what object could you use to connect all 3 of those points to make them become part of the same thing? Does that make sense?
No, could you explain that again?
So if I, like this, let's say this window, this glass right here, if I put a point here, and a point here, okay? Now I can't draw a line to it, but what object could I use to connect all the points? Okay, a triangle, okay, very good, so we're getting there. Yes, so could it be a triangle, could it be a square, a rectangle that would, let me ask you this, does it have to be defined to where it can't go beyond those points? You see what I'm saying? Let's do this. These are dry erase, so they should come off, and they do. They do, okay? So we have 3 points here, like this. okay? They do not connect by one line. But let me ask you this. What if I were to somehow connect them, just make them connect to one single object, and I did this? Are they connected? Like, do they all touch the same object? Sure. So I used even a piece of paper would be able to make sure that they all touched, or were all part of the same system. Okay? Likewise, out there in the where the flagpole is, all those rocks help connect the same system, the flat plane. Okay? So a line is made of 2 collinear points. A plane is made of 3 non-collinear points. And then finally, space contains at least 4 non-collinear points. So you have a 4th point, and so once that 4th point exists and they're not in conjunction with each other, or even the point can come way out here, it can extend beyond these 3, then you have space. Now this is what's interesting. Try to tell me 3 points that you could put anywhere, use your hands or whatever if you want to, that could not be connected by a sheet of paper, no matter what size the sheet of paper is. Okay? So, now if you think about it, you have those 3 points, okay, there, and back there. You can actually end up laying some sort of paper on there, okay? Because paper can rotate back and forth. If you throw in a 4th one in there, well, then there's absolutely no way that, especially if they're non-collinear, that you can adjust that piece of paper without bending it to make it touch that 4th piece. Does that make sense? So these 3 points can actually rotate in any direction, and it's still a plane. If you throw a 4th point on there somewhere, it may end up being on that plane, but could actually extend out here. And where you have this, how do you touch this piece of paper to this point out here? Well, that's whenever you create space. That's where dimension actually begins to exist. So we're not going into that a whole lot, other than just understanding its possibilities, okay? Because then we go into all sorts of craziness. Okay, so then we have our line postulate. Any 2 points in space lie in exactly one line. We've got that. Plane postulate. 3 distinct non-collinear points lie in exactly one plane. And then a flat plane postulate is if 2 points lie in a plane, then the line containing these 2 points lies in the same plane. Do you know what that means? So if 2 planes, we take that 3rd point off this window. Now we have these 2, and that lies in a plane. Okay, then the line that makes those 2 points, that connects those 2 points, also lies in that same plane. Makes sense, right? Does everybody understand what I'm saying?
Yeah.
Okay, awesome. So you're like, oh, well, that's easy enough. And that is going to be the difficult part. I say the difficult part. Difficult and interesting part of this class is you're going to be finding out things that are like, well, that makes sense. But then if you think about it for a second, I've never really thought of it that way before. And this is going to force you to think of things from that perspective. And then the plane intersection postulate. If 2 planes intersect, then what do you think will exist when they intersect? What do you think they create? So let's think of this. Take 2 lines and intersect them. Okay, 2 lines and intersect them. You can even use your fingers. Hold your fingers and make a cross. Okay? Now, whenever you cross your fingers, what do they actually make that are in common with each other?
2 lines.
Well, they have 2 lines, but they're not the same 2 lines. One's going one direction, one's going another, but they cross at what?
1 point.
1 point. So 2 lines intersecting create 1 point. Now, what happens when 2 planes intersect? What do they create?
A big point.
Well, kind of. You're not too far off from that, a big point. So open your hand flat, and now karate chop it like dissect your hand with your other hand. There you go. Makes a line. Very good. All right, so two planes that intersect end up making a line. And two lines that intersect end up making a point. Pretty interesting, right? Cool. So, and what's interesting about all this is it takes, if you look out there in the real world with all the ants and everything, people, cars, all that stuff moving around, running around, it takes these basic concepts to make those things exist out there. We have to have these definitions so that consistently we have cars that function, consistently we have buildings that stand, we have roadways that actually make sense, we have places for people to walk and for us visually to be able to see what's going on out there. So even though some of this stuff is basic, if you took it for granted and didn't have definition, then it would be utter chaos. So, all right. We also have incident theorems. We're actually... Okay, I'm just going to go over what a theorem is. Theorems are statements that can be proved by a logical progression of definitions, postulates, and previously proven theorems. Okay, so stuff that already exists, you can take those to either prove or disprove something that you're trying to discover or substantiate. And that's all that really is, an incident theorem. Okay? And that's pretty easy. But what you end up having to do is doing research. Okay, you have to already know what your definitions are or how to find them. That's just as important. Even if you don't know them, know how to find them. And then you can go through and determine if that incident theorem is actually accurate or false. So on the last section, 1.7, I want you to write down 3 things. We're going to have definitions because we're talking about sketches and construction. First of all is a sketch. Okay, a sketch. Write down the word sketch. Okay, a sketch is a freehand picture using only a writing instrument, like a pencil or something. A freehand sketch. I'm sorry, it's a freehand picture. I'm sorry, or a freehand picture. Yep, just using a writing instrument like a pencil or a pen or crayon or something like that. Now, only using your pencil, I want y'all to sketch, underneath your definition, sketch a rectangle. Okay? Easy enough, right? Y'all just sketched it. It was cool. Right? Wasn't that fun? Like you sketched it. Sketched it. You're the most sketched it thing I've ever seen. Something like that. So notice that now, what's really interesting to me is how many of you look down at your rectangle. Are you proud of your rectangle?
No,
Why?
because it's all.
Okay, so what would you have rather used? Well, I'm sorry, are you proud of your rectangle? No? It's okay if you are. You don't feel compelled to say no, so.
It's not the best rectangle I've ever seen.
How about you?
Yeah, I followed the line and then made 2 lines on the other line.
Okay.
So I made it.
Cool, you did the best with what you had, right? And what's interesting, there are some people that it drives them nuts. Me, I like using straight edges. I hate it when my stuff is out of sorts and out of order. There's a squiggly line that just messed everything else up. That bothers me. But there is another method of creating pictures using that involve instruments, and that's where we're going to go to next. So we have, next is a drawing. Okay, a drawing. A drawing is made with the aid of tools. And the tools can be a ruler, protractor, compass, a T-square, drafting triangles, whatever. I mean, you kind of get the idea. You can use what's called a French curve. You don't have to write all these down, but just understand, like, yeah, just list a couple of instruments that you could use, okay? By correctly using these instruments, you can make drawings that are quite accurate. So if you think about it, if you had a ruler and you wanted your rectangle at a specific dimension, then you can use that ruler and make it very, very specific. Without that ruler and you're just using a pencil, you're kind of guessing if it's accurate or not, right? And then the edges may not be straight. It may end up being a rhombus, not an actual rectangle, or it may end up being a perfect square or something like that. It just kind of depends. So a drawing helps us with our accuracy. A sketch is just basically freehanding an idea. Now finally, and this is what's going to be kind of interesting, what do you think a construction is? A construction. What do you think it would be?
Can I read the definition?
Hmm?
Can I read the definition?
Yeah, are we in a spelling bee? So, can I get the origin? Yes, so I'm asking though, what do you think a construction is? Do you think it's going to be more accurate or less accurate than a drawing? Okay, what would make it more accurate than using whatever instruments that you needed to? A robot. Interesting. Yes, you could use a
You
robot.
only have 2 options, so it's not as varied.
Okay. Okay, that's true. So by definition, a construction is a drawing, which is interesting that it uses the word drawing, right? Have we already defined what a drawing is? Okay. So under the definition of drawing, we will have the aid of only 2 instruments. 2 instruments, and they're very specific. An unmarked straight edge and a compass. And by compass, it's not a nautical compass or a directional compass. It's a mathematical compass.
What were the things?
An unmarked straight edge and a compass. And a compass is those 2 legs, one that has a metal or some sort of point at the end of one, and then the other has a pencil on the other end. If you open your book, you can see a picture of it on page 33. And here I'll show y'all. Yeah, you can show everyone if you'd like. That's what a compass looks like. No, y'all have seen them before. So now notice it doesn't say a pencil as part of the tools that are used, because the pencil being used is part of the compass. So we only have that and an unmarked straight edge. Okay, the straight edge, and then we'll be done with class, but I'm going to read off these last couple paragraphs. The straight edge is used only for making straight lines through 2 points. Okay, so you've created your 2 points using specific distances on your compass. The straight edge is only used to connect those 2 points or to draw a line going through them. Okay, the straight edge cannot be used in any way for measuring, which is why it's an unmarked straight edge. With regard to construction, measuring using like a ruler is cheating. So you're cheaters if you use rulers, and you know what happens to cheaters? Huh?
Well, they win sometimes.
Cheaters always lose. What?
So will they sometimes win?
Well, no. Cheaters, you stand out in parking lots and people throw rocks at you. That's what happens to cheaters. So don't cheat in math class. So, yeah. So, I know, it's violent math class. So straight edges cannot be used in any way for measuring. Okay, the compass is used to make circles and arcs to mark off segments of certain lengths. What's interesting is, and we're actually going to work on, next class, we'll work on using your compasses, so bring them next class. And we'll show you how to make arcs that intersect. And just like what happens when two lines intersect, what do they make? A point. Same thing with two arcs. When two arcs intersect, they make a single point. So you're making a series of points using your compass all over the page, and then you can mark lines through those points using your straight edge. And then you end up constructing an actual object. Okay? Constructions are important in the study of geometry because they help you see clear physical relationships that are models of mathematical theory. And if you understand these physical relationships, you will better understand related mathematical concepts, and constructions must always be accurate and neat. Okay? So real quickly, sketches, they let you make neat freehand pictures. Drawings allow you to use any tools you desire, including rulers, protractors, but freehand is forbidden. Okay? And then construction requires a drawing using only a straight edge and a compass. All right? Cool. Any questions?